That's really cool. You know, I've pretty much always hated golf, and yet I graduated from high school because of golf. So, you know, I guess I have sort of a love-hate relationship with golf. The winds were crazy, weren't they? I know. And James was like, should I ask her to tell me what that story is? Yeah, I don't know. Maybe I'll tell you sometime. All right, it looks like we got a bunch of people here today, and I think I've given everybody record permission. Could be wrong, but I think I've got everybody clicked. Click, 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 click. So today's topic, main theme for today is heat. Heat and temperature, and how heat is distributed throughout lakes, how heat gets into lakes and leaves lakes and moves within the lake, how different lakes are different with respect to heat, and how the different times of year are different, again, with respect to heat. I think what I'm going to do is I got a PowerPoint, and I figured I'd lecture and tell you how it is. And I got a couple questions for you to work on, but maybe we'll make sure everybody's here or the latecomers have a chance to arrive. Maybe I'll just start with sort of a basic definition up here. And that is to say, what is heat and what are the units of heat? And how is that different from temperature? So heat and the units for heat, and temperature and the units for temperature. I'm sure that you have learned this before, probably, but maybe it's faded in your mind and those things have kind of coalesced, and yet they're separate. So just to kind of get a sense of where we're at to start with, let's have some little breakout rooms with 2 to 3 people in a room. Nobody's depending on Jeffrey. I just want you to just discuss, come back with definitions and units for heat and temperature. And there's just 2 people in the room, so it's like you're sitting at a table and you find that you're sitting next to James, you're sitting next to Kat, whatever. Turn to the person next to you, see if you can agree. What is heat? What's the definition of heat? What are its units? And what is temperature? Definition of temperature, units of temperature. Okay, so this is just an icebreaker, so to speak. So please join the room and come back with answers to those 2 questions.
So I kind of forgot the unit for heat, but I'm pretty sure the unit for temperature is Kelvin.
Yes, it is Kelvin.
Hey, what was the question exactly as far as heat goes?
Yeah, so she was asking like what's the definition of heat and like the units of heat and what's the definition of temperature and the units of temperature.
Oh, okay. Is it joules then? Or
Yeah, I
heat?
feel like joules would be the right answer for
I think
units.
s- Yeah, I think so. As far as like heat capacity or something, or yeah.
Right.
Specifically. Cool.
And then like joules are just like how many calories are used to up the temperature of something.
Yeah. How many? Yeah, I can't remember now.
It's just bringing me back to chemistry, but
Oh yeah.
yeah. In the book, it talks a lot about like thermoclines and all of that. Monolimnion. Trying to figure out if the heat's more in like the first part of the chapter or the last part.
Yeah. I'm only saying like temperature as a factor, or I don't know. I'm not saying
Yeah, right?
about joules. That's for sure. I don't know.
I think it might just be like prior knowledge that she's asking us to
Yeah,
have.
yeah. I think so. I would be kind of surprised to see. Or I don't know.
But I mean, temperature is just like what is the heat within a space,
Yeah,
really, right?
right. Yeah. Oh, okay, bye. See you.
All right, looks like we got everybody back. So let's start with our opening question, which is what heat and temperature, what are they? We had that's really two questions, and we got 5 rooms. So let's see who can start us off. Well, let's start with room 1. Zoom says Brett, Kat, and Tiffany were in room 1. Answer any one of these. What is heat? What are its units? What is temperature? What are its units? Your choice. Answer one of those.
Well, for temperature, the units would be Celsius.
Okay, so I'm going to say that's true, but let's start with Kelvin. Oh, which I can't spell. Wait a minute, Kelvin. And the reason we're going to start with Kelvin is because Kelvin is the one that's actually really meaningful in the sense that 0 Kelvin really does mean 0 temperature. Whereas 0 Celsius is just the freezing point of clean, pure water at the ordinary Earth surface pressure. So we will use Celsius. And you really also need to be familiar with Fahrenheit. Scientists use Celsius. The general public in the United States uses Fahrenheit. Limnology is kind of in between. Sometimes you got to use science, and sometimes you got to talk to people. So, anyways. But Kelvin is really the root of it all because 0 Kelvin means no temperature. Yeah. All right, thank you. Let's go to room 2. We got the Sam and Saul in room 2. Which one would you like to pick? You got heat, define it, units, or define temperature.
So I would say that heat is energy.
Energy?
Yep.
Do you know what kind of energy?
Thermal.
That's good. That's good. I like that. Yeah. Heat is kinetic energy. Of atoms and molecules. We use joules, especially chemistry and physics, whereas ordinary people are more likely to understand calories as a unit of energy. And you need to be able to understand that both of these are energy and that there's a relationship between them. Anybody want to tell me what's the relationship, the conversion between joules and calories? Anybody happen to know? No, 1 calorie. I mean, which is more heat? A calorie or a joule? Which is bigger? Which is more heat?
Calorie.
Calorie. Yeah. So like if you were freezing to death and somebody said, well, I could give you 100 joules or I could give you 100 calories. Which would you choose?
Calories.
Calories, yeah. So about how many joules are there in a calorie? 2, 3, 4, 100, 1,000, 10,000?
Isn't it like 4.184?
So with greater precision than we really need, I think it's 4.187. But you could correct me, anybody who's been in chemistry recently or is like, Googling on your phone while we're talking. Yeah. So both of these are units of energy. And energy, of course, energy is the ability to do work. And as I think I've mentioned, there's really only 2 things in the world. Like in the entire universe, there's really only 2 things, right? There's matter and there's energy. And that's it. And if you go to really, really fine scales of things, you discover that matter, the tiniest little particles of matter, are actually energy, right? Subatomic particles. If you get all the way down to like the quark level and stuff and you split stuff, yeah, you discover that actually there's only one thing in the universe, matter or energy, depending on how you look at it. Anyway, the units for energy are a calorie or heat, and I will use both of them. I like calories personally because I can relate to a calorie in a sort of a intuitive way that I find harder to do with joules. All right, so heat is a kinetic energy of atoms and molecules, moving from place to place, spinning, and vibrating, right? So there's different forms that the energy can take. It can be literal movement from one place to another, flying around like crazy. It can be spinning, or it can be a molecule vibrating, like those bonds, like back and forth and back and forth. Yeah. Okay, and all of that is what heat does. You add heat and you get more movement of the molecules. Okay, and like we're not a physics class, right? So this is just like the limnology looks at heat. Limnologists look at heat. Okay, so what is temperature? And that leaves it down to Desiree, James, or Keenan. What is temperature? Definition.
We said it was like a measure of how hot or cold an object or something is.
Yeah, but that's kind of circular, right? Because the definition of hot is higher temperature and the definition of cold is lower temperature. Okay, so yeah, it's not wrong, but how is that different from heat? It's okay, you can tag somebody else, you know. Hey, James Keenan, what's the definition of temperature?
We said something similar, the degree of heat present in a substance or object. So I guess the defining bit would be that it is present in a substance or an object.
Yeah, okay. Well, but heat doesn't exist in the absence of a substance or object, right? Heat is the kinetic energy of atoms and molecules. So if there aren't any atoms or molecules, there's no heat. There could still be energy, like electromagnetic waves, but it wouldn't be heat. Yeah, infrared light is not heat. Just clarifying that. Okay, so anybody, what's the difference between heat and temperature? I'm rejecting your explanations, but I know you guys can take it, right? You're not like, I'm not hurting your feelings, right? Okay, just checking. So what is temperature? All right, temperature is essentially the amount of heat divided by the number of molecules. So it's the average kinetic energy per atom or molecule. Typically people say molecule. So in a sense, if you're going to say that heat is kinetic energy, you could say that temperature is the average heat per molecule. Now, this is an important distinction. And one of the reasons it's important is because a lot of people don't actually know the difference between heat and temperature. And obviously, if you don't know the difference between two things, you're going to have a hard time understanding the relationship between them. Because in part of your brain, they're not even different things, right? So heat is the total amount of energy, and temperature is the amount of that amount of heat divided by how much stuff you have. All right, does that make sense? Why don't you give me a little check mark if it's kind of like you're like, I learned this before, I thought I would never see it again. If this makes sense, kind of give me a little check mark. If it doesn't, give me a little red X. I'll take a look at how we're doing. Looks like everybody who voted yes. So then let me ask you this question. Which has the higher temperature? I got 2 jars of water here, by the way. Here. Here's 500 milliliters of water. Warm tap water. 500 mils. Here is slightly over a liter of warm tap water. Okay, so here we have bottle number 1 and bottle number 2. So my question for you is, which one is the higher temperature? Number 1, number 2, or they're equal? You know, neither or both or whatever. Which has more heat? All right, so I just, while you guys were doing that first thing, I went over to the sink. I filled this up with hot water from the tap. And in the blink of an eye, I filled this one up with hot water from the same tap. Okay. Any questions about the questions? I went to the sink. I filled this, I'm in the basement, so it's the laundry sink over there, right? I filled this up with hot water. In the blink of an eye, I filled this one up from hot water, same tap. Which has a higher temperature and which has more heat? Number 1, number 2, or they're equal. Okay, so I got 2 questions and I got some 2 or 3 people discussion groups. It's really just you're sitting at a table. So turn to the person you're sitting next to and answer those 2 questions, okay? There you go. This is a quick question.
So temperature is average, like kinetic energy, right? And then heat is the kinetic energy of atoms and molecules?
Yeah.
Is that
Yeah,
okay?
so yeah.
So would the temperature be the same, but the heat would be more for the one that had more hot water in it?
I think assuming it's kind of a tricky question, I guess. Well, the her definition of temperature was like heat per molecule or mole. So like I think technically since it would be like a bigger denominator for the larger volume, it would be a lower temperature. But that's just my because if they have the same amount of heat theoretically,
Yeah.
then it'd be a bigger volume. But I don't know because my first thought would be that it would be the bigger one because the bigger one would like the heat would diffuse slower out of it. I don't know.
So you're saying the bigger one has less heat, or are you saying the bigger one has more
Yeah,
has less heat?
less heat. Yeah, but I
Yeah.
don't know.
And then for temperature, what would you say for that one?
Um. Oh, that would be for temperature. Sorry. So for temperature, because it's a
Bigger.
smaller volume, it would be bigger temperature. I don't know that they're. I
Well,
think that
smaller
we assume.
volume, bigger. Yeah, that makes more. Yeah, that makes sense. Yeah.
Oh yeah.
Instead of it being the same, because you've got. I hear you on that one. For that, yes.
With the volume, cool. Yeah, I guess I never thought of it like that way though.
Me neither.
But I have taken chemistry. So.
Yeah.
Too much chemistry. Okay, see ya guys.
All right, welcome back, everybody. And now we're going to do a poll because I think that'll be fun. And the way the poll is set up is answer number 1 on the poll is this. Answer number two, and then number 3 is both. Are you ready? So question is, which has higher temperature? 1, 2, or both? So hopefully, we'll see if this works. Yeah, it's a scale of 1 to 5, but whatever, just ignore questions 4 and 5. So place your votes now. Which has the higher temperature? This one, or both? Votes are rolling in. Yeah, the first question is, which has the higher temperature? I got 12 out of 13 people have voted. Oh, I suppose Jeffrey might be, let's see, can Jeffrey vote? Maybe not. All right, we're gonna end the polling here. And wow, clearly we need to go over this because share the results. Over half the class is wrong. Okay, maybe the question wasn't clear, but I mean, I went to the hot water tap and I filled these two things up with exactly the same water. They're the same temperature. I don't know what that temperature is. I don't have a thermometer right here, but I mean, these are exactly the same temperature. Same hot water, same tap, same moment in time, same temperature. All right, let's go to our next question. Maybe you'll do better on this one. So these two jars are the same temperature, but this one has like 3 times as much water in the jar. Ooh, I don't know, does that make any difference? They're the same temperature. Okay, so which of these has the higher, which of these has more heat? Number 1, number 2, or number 3, they are the same. So I'm going to relaunch the polling, and now we're doing the second question, which has more heat? Relaunching the poll will clear existing results, yes. Okay, place your votes. Which has more heat? Okay, I got 10 people, 11 people. Which has more heat? The little jar, the big jar, or they're the same? All right, well, we got 11 out of 13 people have voted. And yes, you did much better on this question. These two things are the same temperature. They have the same average kinetic energy per molecule, but there's a lot more molecules here. Therefore, there is more heat here. Now, what I mean by the same average kinetic energy per molecule is this is entirely water. This is entirely water, H2O. And, oh, yes, share results. Hey, much better, much better. It's entirely water. And if we're saying they're at the same temperature, what we're saying is those water molecules are moving just as fast. These molecules are moving just as fast inside here, slamming around, bumping into each other, rotating, vibrating. These molecules are moving just as much as these molecules are, but there's a lot more of them here. Well, given that there still seems to be like there might be some confusion about the relationship between heat and temperature, let me give you just a visual example. I got a heater here, a little space heater, and when you plug it in and you put it on high, number 2, this thing's got 1,000 watts. It's 1,000 watts. Now, a watt, watts, like light bulbs, watts, right? A watt, 1 watt is 1 joule per second. This thing is, when you put it on high setting, releases 1,000 watts, 1,000 joules of heat, 1,000 joules of energy every second. That's what 1,000 watts means. So if I took this heater and I turned it on, which I'm not actually gonna literally do this, but you can imagine me turning this on. It's like really hot, which is nice. It's releasing 1,000 joules every second. I could put this jar of water on it, make a little funnel out of aluminum foil or something, right? so that all of the heat goes into this water, so that this water was gaining 1,000 joules every second. What's going to happen to the temperature of this water? Is it going to go up? Is it going to go down? Or is it going to stay the same? You could just speak or put it in the chat. What's going to happen to this water? The temperature of the water. Yeah, it's going to go up because I'm adding heat to it. If I add heat to it, the temperature will go up. What if I did the same thing with this jar of water? I got a aluminum foil casing here so that all 1,000 joules per second are going into this water. What's going to happen to the temperature of this water? Is this going to go up, go down, or is it going to stay the same? Yes, exactly. The temperature of this water is going to go up, but it's going to go up more slowly than the temperature of this water. I mean, you know that. If you want to boil water on the stove, you don't really put more water in than you need, right? Because if you fill the pot full, it takes longer to warm up than if the pot's only half full. So, I mean, I think you know that sort of intuitively. In fact, you could actually calculate exactly how much longer it would take. If this is twice as much water, it's only going to rise in temperature half as quickly as this does. Or in other words, if this is half as much water, it will rise twice as fast. Because a joule, 1 joule per second. Let's say that, okay, let's not do any math without writing numbers down. So let's move on. I guess the point is that temperature is the average kinetic energy, and heat is the energy. And if you have something like a heater, it's going to put out a certain amount of heat at a certain rate, so many calories per second, so many joules per second. The sunlight comes in and delivers a certain amount of energy per second, per square meter. So different things heat up differently in the sunlight. You get a tiny little ice cube, thin little film of ice. It's going to melt really quickly. Same sunlight, great big thick cube of ice, melts more slowly. Raising the temperature is different from melting something, right? Seems like we need some technical terms. So let's go to the PowerPoint. All right, everybody ready? Any questions before we dive into the PowerPoint? All right, well, let's start off. Let's talk about heat in lakes. Now I have 2 PowerPoints, and I'm probably gonna start this one and then stop in the middle to go do the other one. This one is very general. This is about the properties of water with respect to heat, temperature profiles, and isopleth diagrams, and the 4 seasons of lakes. And then the other one, which is shorter, is really focused on ice, lake ice, and heat transfer. Okay, so let's start with water. Properties of water. All right. I was kind of surprised that, everybody didn't get all these questions 100% correct on the midterm exam. I mean, obviously you learn about water many times, including in chemistry classes. But let's just go over this again. And this will be the 3rd time's the charm for somebody. So what we have here is just a classic graph. Temperature is on the x-axis. Temperature in Celsius. And we like Celsius as humans. We like Celsius because it's meaningful to us in our experience of the world. Like, you know, freezing is a big deal for us. Freezing of water. So we got 0 degrees Celsius on the left. That's the temperature at which pure water freezes. And then it goes, as you go from left to right, the temperature goes up. And here's like 10 degrees. You know, that's like 50 Fahrenheit. The vertical axis here is the density of water. And you can see that the density of water is really close to, it's really close to 1,000 grams per liter, the density of water, 1,000 grams per liter. Now, how many grams of water, did I say that right? Yes, how many grams of water are there in a liter? Oh, okay, that's kind of obvious. How many grams of water are there in a liter? Like about 1,000. A liter of water weighs really close to 1 kilogram. 1 liter, 1 kilogram. 1 gram of water, that's 1,000th of a kilogram, has a volume of about 1 milliliter, 1,000th of a liter. You need to know that. I mean, you need to know that. That 1 liter of water has a mass of real close to 1 kilogram. And similarly, 1 gram of water has a volume of really close to 1 milliliter. Okay, but it's real close to, but it varies with temperature, right? As you heat the water up, it expands. As long as you're above 4 degrees, if you warm the water up, it expands and its density drops. If you are below 4 degrees, however, and you, let's say the water is 1 degree Celsius, and you warm the water up, what happens to the density? If you have water that is 1 degree Celsius, and you add some heat to it, so you warm it up, does it expand? Does it contract? Or does it stay the same volume? You have 1 gram of water, or whatever it is, at 1 degree Celsius, and you add some heat to it. Does it expand? Does it contract? Or does it stay the same volume? You can just put that in the chat, get a couple of answers. 1 degree water, and you warm it up a little bit. Does it expand? Does it contract? Or does it stay the same volume? Take a guess, put it in the chat. I got three people have guessed. Just make a guess. 1 degree water, add some heat. Does it expand? Does it contract? Or does it stay the same? All right, so what we've got is we've got 1 degree water. It's got a density of, 999.9 grams per liter. We add some water to it. We add some heat to it, right? So we heat it up. What happens to the temperature? Oh, look, the temperature, What happens to the density? Oh, look, the density went up as we added heat to it. The density went up. That means it contracted. The mass didn't change, therefore the volume must have gotten smaller. If you are less than 4 degrees, adding a little bit of heat increases the density. Adding a little bit of heat decreases the volume of the water. Okay, now that's really weird. That is the opposite of what you would expect. Anything normal, you know, here it is, you add some heat to it, what happens to it? The density drops. You know, you heat things up and they expand. Not true for right here. In between 0 and 4 degrees, water contracts as it warms. Now that's because ice is this very orderly crystal of water molecules, right? When water is a liquid, the water molecules are moving around, there's little hydrogen bonds connecting them, you know, and so on. They're fairly close together, you know, as the liquid. When it becomes ice, they push apart into an orderly lattice and stop there. And so going from a liquid to a solid involves a little bit of the molecules pushing away from each other. In other words, going from liquid to solid involves a decrease in density, an expansion of the volume. That's really important because like everybody knows it, and sometimes it's valuable to know about water, and it's really kind of almost unique, not entirely unique. There's like 2 other liquids that do this, but you know, it's not entirely unique, but it's really rare and it's really cool. So you need to know it. And sorry, I'm gonna erase my, are there any questions about that? Hey, there's a good question, Desiree. Yeah, we'll get to that. So first of all, we have the density of water, the relationship between temperature, heat, and density. You add heat, it raises the temperature. If it's a normal thing, you're adding heat, you're increasing the temperature, the water molecules are moving faster, and faster means they're going to typically be farther apart from each other. When they hit each other, they recoil more, right? So, you know, there's more energy, it tends to cause them to, molecules to spread out more, expanding the liquid. Except between 4 and 0 in water, because of water's curious way of settling into a crystal, I would say. Now, here's the density of liquid water. Here's the density of ice. And you will recall that ice is incredibly less dense than water. If water, liquid water, has a density of very, very close to 1 liter per kilogram, I say that right? Very, very close to 1 kilogram per liter, 1,000 grams per liter. The density of ice is down near less than, you know, down near 920 kilograms, 920 grams per liter. In other words, it's like 8% less dense. The difference between 100 and 920 is the difference between 10 and 9.2. Okay. All right. So there's liquid water here. Here's ice. There's 0. Okay. I'd like to point out that the density of ice, as ice gets colder, like any normal substance, it contracts. And as it gets colder, therefore, its density increases. And I think I'm going to come back to this, and let's go to the next one. And okay, so this is from the engineering toolbox online, which is where I get random factoids. Okay, seawater is like lake water, except it's got like 30 grams of salt in it, 35 grams of salt per liter. And when you add that much salt to water, first of all, you make it harder for it to freeze. If you add salt to water, it's harder for it to assume that lattice, that orderly lattice-like shape. So you have to cool it down even further to get it to chill into ice. So the freezing point of seawater is lower. Furthermore, the sodium ions and the chloride ions, the sodium chloride, the salt in the water, interferes with the hydrogen bonds, with a result that, I guess that would be, yeah, that's a short way to say it, with the result that there is no maximum, there's no temperature of maximum density above freezing. Seawater does not have that curiosity of a maximum density above the freezing point. For seawater, the temperature of maximum density is the melting point, the freezing point. And as you can see, seawater is more dense as well. Those sodium and those chloride ions nestle in between the liquid water molecules so that the same volume contains more mass. All of those water molecules plus those sodium and chloride ions kind of in between the water molecules. So the density is higher, there's more mass per volume. Okay, Desiree requested that we talk about specific heat. You read my mind, right? Specific heat and the heat of melting and the heat of vaporization. So here we go. How much heat does it take to raise 1 gram of liquid water 1 degree Celsius? And you know this, but you might not know how much heat does it take to raise 1 gram of solid water 1 degree. You might know this. So I got 4 blanks here. I remember calories. You might remember joules. If you've got one, you can calculate the other. So I got 4 blanks here. Please try to fill them in. How much heat does it take to raise the temperature of 1 gram of liquid water 1 degree? How much heat does it take to raise the temperature of 1 gram of solid water 1 degree? And I'm going to put you back in your so productive groups to answer these questions. Just give you 3 minutes. Come back with as many of those 4 as you can come up with, at least one of them. And from one, you can calculate the other. The third is a little harder. And from that, you can calculate the fourth. So please try to come back with 4 numbers.
Does anyone have any ideas on how to go about this one?
Not a clue.
Yeah. Yep. Again, this is like chemistry, so it's reminding me of those questions about specific heat and how to calculate it, but
Definitely done like 1,000 times, but for some reason I'm just. I mean, I think it's 1 calorie per degree per gram per degree for liquid water, but it's more for ice. I'm trying to think of like the heat of vaporization. I don't know. Maybe I'm thinking too hard or overthinking it.
yeah, no, it's you're in the right area of where I was going to. I just don't remember the digits or numbers. So
Well, I guess we'll see.
All right, welcome back. Well, let's get some answers on the table here, so to speak. And what's going on here? Okay. So you might recognize this number as the specific heat of water, which is a funny word, but that's the heat that it takes to raise water by 1 degree. And the answers are, hey, where are my answers? Hey, where's my answers? Hey, I feel cheated. I set up this PowerPoint with answers in it. Just a sec here. I'm gonna stop ranting. What are the answers? Well, the answer is 1 calorie per gram for liquid water. So 4.187, 4.167 joules. It's not exactly that because it's not pure distilled water if you're talking about lake. So frankly, for joules, you should probably say 4.2 joules, or maybe 4.1. Anyways, what about solid water? Sorry, here we go. Specific heat of ice, right, is about 2 joules per gram or 2 kilojoules per kilogram. And this is joules. So in other words, it's about half. And I think that what I have to do on here, apologize for the technical challenge here. Oh. Well, I lost my numbers. I'm really sad here. Okay. All right. Well, anyways, so that's specific heat. So 1 calorie to raise 1 gram of liquid water, it's about half a calorie for solid water. The specific heat of ice is less than the specific heat of liquid water. And in both cases, the specific heat actually changes with temperature. So when we say that the specific heat of water is 1 calorie or, whatever, 4.187 joules or whatever, that is when the liquid water is at 15 degrees C. The specific heat actually varies a little bit with the temperature. But you want to memorize one number, that's the one you memorize. Similarly, the specific heat of solid water varies with temperature. And it's typical to quote it at a temperature of -10 Celsius, because at -10 Celsius, it's an even 2 joules per gram, 2 kilojoules per kilogram. So that's very easy to remember. Okay, the next question is the amount of heat it takes to change 1 gram of solid water to liquid, and to change the 1 gram of liquid to vapor without changing its temperature, just changing its phase. I lost the numbers here, which would make it easy, but the question I have for you is this. These numbers are both bigger than 1. They're both bigger than 1 calorie per gram. But which of these two is bigger than the other? Does it take more heat to melt a gram of ice or to completely evaporate a gram of liquid water? Which of these two is bigger? The heat to melt a gram of ice or the heat to evaporate a gram of liquid? Which of these two is a bigger number? Yes, the heat of vaporization, the amount of heat it takes to evaporate entirely a gram. This number is like 80 calories, 80 calories, and this is a couple of 100 calories per gram. Okay, which is why like sweating is so effective, because so much heat gets lost when the water evaporates off your skin. Okay, well, let's move on. During the break, I'll look for where my numbers went. But anyways, you can look the numbers up. Okay, let's talk about lakes. Okay, so we understand that as long as you're above 4 degrees, warming the water up makes it less dense, right? And we understand that when you shift from liquid to solid, then ice has a way lower density than liquid water of any temperature. So what we want to do now is think about how does this affect lakes? This is really different from like, you know, being a worm living in the dirt, or, you know, being a bat or a butterfly flying around in the air. If we're thinking about lakes as a place where things live, the properties of water are really important. And these are the properties that create the 4 seasons of lakes. So that's kind of where we want to go. We want to understand the 4 seasons of a dimictic lake. We want to have a better understanding of ice cover, spring mixing, summer stratification, fall mixing, winter ice cover, you know, and so on. All right, well, let's look at temperature profiles. Limnologists look at lakes in this kind of way. A vertical axis that is the depth in the lake. The top of the graph is the surface of the lake. And as you go down the graph, you're going down into the lake. This is the standard organization of axes for limnologists. If I give you an exam question and I say, using standard limnological axes, this is what I mean. Draw the graph the way a limnologist would draw the graph. The vertical axis has 0 at the top because that's the surface of the lake. And as you go down, it goes down into the lake. The horizontal axis always goes from left to right like you're used to, but it's always at the top of the graph because that's where the 0 is for the y-axis. Okay, so this is the way limnologists look at lakes. And what we want to do is think about the temperature profile in a lake in the 4 seasons. Now, we're talking about dimictic lakes. That is to say, lakes that mix twice a year in the spring and in the fall. The mixing is broken up in the summer by the lake being stratified. And the 2 mixing periods are separated. Spring and fall are separated by the winter when the lake is ice covered. If the lake doesn't get ice covered, then the fall mixing just kind of runs into the spring mixing, and we say the lake is monomictic. If, on the other hand, like an Arctic lake, the lake is ice covered most of the year, and in the summertime it never stratifies, so that the spring mixing and the fall mixing are just all connected to each other, one long mixing period, well, actually short, then we say the lake is monomictic. In the first case, we say it's warm monomictic because it never gets ice covered. And in the second, we say it's cold monomictic because it never stratifies, or it never stratifies. Okay, so we're going to talk about dimictic lakes, and what I want you to do now is practice. You gotta learn how to draw these diagrams. So what I want you to do is I'm going to put you in a discussion group, and I'm going to ask you to, if you can, try to remember what is the shape of each of these time periods. What is the shape of the temperature versus depth line in the spring mixing period? How is it shaped in the summer when the lake is stratified? And fall mixing, and then how is it shaped in the winter when the lake is ice covered? So what I'm gonna maybe put you in slightly larger random Zoom rooms now, because you need someone who can draw these 4 diagrams and somebody else who can tell them what to do, and somebody else who's going to chip in on that. So your assignment in your group is to come back with 4 charts, 4 graphs like these, with the axes in the correct orientation, and okay, and at least a sketch of what is the shape of the temperature depth, the temperature profile. Okay, so we're going to have some new rooms. We want, at least 3 people in a room. And let's make sure nobody's really depending on Jeffrey. 3 people in every room. Okay, so come back with 4 graphs.
What?
Hi, Sam.
Hey. Let's see. Should I just make the 4 graphs first?
Sure.
Oh, wait. Can you make lines on this?
I think so. This is the one, you have like you have the cool screen, don't you? Or is this
The
yours?
white?
Yeah,
The
is this
whiteboard? Yeah.
Yeah, I think there's lines. Yeah, look at
I
that.
got it. Why is this green?
So I was thinking for the, I don't know, for the mixing parts, the temperature profile would pretty much
Just,
be consistent.
I think it's like a straight line, isn't it?
Yeah, that's what I was thinking.
Let's see. I think
Stratified would be like hot up top but cold at the bottom. Yeah.
that is it opposite for ice covered.
Yeah. Hot at the bottom and cold up top.
Is that all we should add? You think? Or I could add some labels.
I feel like she's gonna.
Oh,
I think it'll be fine. I think that's fine.
okay. Oops. There we go.
All right, welcome back, everybody. So who would like to give a shot and show us your diagrams? Jeffrey said that the people in his room were drawing some good looking diagrams, so maybe we should start with room 3, which would be Kat and Sam T.
So this is what we had for the graphs.
Excellent. This is exactly what I'm looking for. All right, I hope all of you came up with graphs that look like this. Just hold it there for a sec if you could.
Yep.
Some mixing. what we've got is isothermal, same temperature, top to bottom. When the lake is stratified, you've got a warm layer on top and a colder layer down below. When it's mixing, same temperature, top to bottom. That's what we mean by mixing. We mean mixing, same temperature, top to bottom. And ice covered, you know, it's some kind of unknown, but below freezing temperature in the ice, warms up rapidly under the ice, and then is basically the same temperature all the way down. So that's kind of just our cartoon version. You know, no numbers on these graphs, just the big picture of the patterns. Any questions about just sort of the big picture pattern? Because we want to know what is it that creates these patterns. Okay, so hopefully you can fix these patterns in your mind. And let's go back to the PowerPoint. Oops. Somehow lost its setting here. Okay. Share my screen, temperature profiles. Okay. So we want to really know what these profiles look like and then understand what is it about water that creates these profiles in lakes. Okay, so we just drew those three. What does it really look like? Okay, well, here's a diagram from this chapter of 5 deep Scottish lakes. And you can see that it's not always that like perfect summer stratification pattern that we've seen, but these are really deep lakes, right? So vertical axis is meters. So these lakes are all, you know, on the order of 50 meters deep. So, well, or deeper actually, 150 plus feet. You can see in terms of temperature, so this is July. So this is warm for these lakes. And you can see that, you know, the upper end of the temperature is 15. These are not warm lakes. You can swim in these, but they're cold, even in the summer. So 10 degrees is 50 Fahrenheit. 20 degrees is like 68 Fahrenheit. So, you know, we're talking about temperatures in the low 60s. So this is chilly to swim in. But all of these lakes, this is Loch Ness, and it doesn't have a great profile, probably because Nessie swims around, you know, and creates turbulence. I'm just kidding, it's imaginary. But this is the lake that Loch Ness Monster lives in. Okay, so just looking at this lake, right? We got an epilimnion that looks to be about 18 meters deep and has a temperature of about 13 degrees Celsius, decreasing slightly with depth. And then there's a kind of a transition zone. And then the hypolimnion is not exactly the same temperature throughout, right? It gets gradually colder as you get deeper. And in the very deepest part of the lake, it's maybe about 6 degrees Celsius. We could look at Loch Awe, which has a very nice profile. The epilimnion, very well mixed, pretty much 15 degrees, top to bottom down to about 10, 12 meters. Then there's a transition zone, the metalimnion. And then the hypolimnion begins at a depth of about 25 meters and is the same temperature top to bottom. Again, about 6 or 7 degrees. Loch Lomond over here on the far right, which is one of the most famously beautiful lakes in Scotland. You can see it has a very gradual drift and not a clear, at least at this date when it was sampled, not a clear epilimnion, hypolimnion, metalimnion. So this is what a variety of real lakes look like, even in the same country, sampled in the same year. And there's just some variations on what stratification looks like. Now, what is it that causes stratification? Well, the point is this: water that's warmer is less dense, and this water is significantly warmer than this water. This water here is significantly less dense than this water. If you were a windstorm and you wanted to push this water down deeper into the lake, you would be pushing this water down, and it would have to be replaced by water that's down here. It would have to get forced up. But that's really hard because, you know, every liter of water here is significantly less mass than this water. And it takes energy to lift mass. So if there's a big density difference, then it requires more energy because you're essentially lifting more mass. Every liter of this water weighs less than a liter of this water. And so if you were to like push one down and the other comes up, you'd be essentially having to lift the difference in weight between the two. Well, that's one way to look at it. And that is, you know, what buoyancy is all about, right? Buoyancy is about the force, the upward pushing force of the water. So if we got an, so here's Jeffrey. Jeffrey's swimming, and Jeffrey's quite buoyant. And why is that? Jeffrey's being supported by water pushing up. If Jeffrey and his mass is being attracted to the center of the earth and pushed down, the only way that Jeffrey could sink in the water was if he pushed water out of the way. But if that water is pushed out of the way and elevated, then it's going to be drawn towards the center of the earth too and pushing back. So the buoyancy is the result of the water that's getting pushed out of the way by the volume of the object. Well, if you're talking about an object or you're just talking about a volume of water, it's the same thing, solid or a liquid. If you've got a volume of water and it's essentially if it were to sink, it would have to push other water out of the way up, that water is going to push back. The greater the density difference, the greater the resistance to mixing. The greater the temperature difference, the greater the resistance to mixing. The sunlight is going to warm the water at the surface of the lake, making it less and less dense. The sunlight is not going to heat the water in the bottom of the lake nearly as much because we know that light is absorbed by water, and it decreases exponentially. The amount of light decreases exponentially as you go deeper into the lake. So much more light is absorbed by this epilimnion water than is absorbed by the hypolimnion water. There's just less light left at the depths of the lake. What that means is if it's sunny, water closer to the surface gets heated up more. It receives more light. It absorbs more light. It heats up more. Well, so, does that make sense? This is what causes and maintains stratification, that the surface water heats up more, and in heating up more, it becomes less dense, less and less dense. And the less dense it is, the greater the difference between the surface water and the deep water, the greater resistance there is to mixing. Now we could look at a chart like this. Now here we have a small lake, little round lake in Ontario. And that is one of those lakes that's not particularly famous, but well studied. Here we have an epilimnion going from, you know, the surface to about a depth of about 3 meters. And the temperature in the epilimnion is about 22, 23 degrees. You can see that the maximum depth of this lake is about 16 meters. And the hypolimnion is probably maybe about 6 meters to the bottom. And then we might call this area in between the metal and neon. What's the resistance to mixing? Let's say that we have a layer of water, like 0 to 1 meters, and below it, another layer of water, 1 to 2 meters. Well, how hard would it be for the wind to mix those 2 layers of water together? Well, what's the difference in temperature? The difference in temperature between the top meter of water, I guess they've got it even finer gradations here. The difference in temperature between the top meter of water and the next meter of water is a very, very small difference in temperature. And these black bars are the resistance to mixing that is caused by the difference in density. These layers of water are about the same temperature, so the resistance to mixing is low or even 0. You get down here into the metal and neon, where the temperature is changing with depth, and you can see that the resistance to mixing, the relative thermal resistance, as they're calling it here, RTR, the resistance to mixing goes up where the temperature difference is greatest, is changing most rapidly with depth. And it's not the temperature per se, right? It's the density that results from the different temperatures. You get down here into the hypolimneon, where from 1 meter to the next, there's only a small difference in temperature. And you can see that the resistance to mixing within the hypolimneon is very low. You will also notice that the temperature in the hypolimneon, it's not 4, that's kind of a myth, right? It's, what would you say? Here's 10, here's 5, looks like this is 6, maybe about 6 degrees Celsius, something like that. Oh, no, that's the relative thermal resistance, sorry. Temperature here 5, actually this does look like it's about 4 degrees. It could be even lower, but it looks like it's below 5. Okay, so that is stratification. And stratification is ultimately the result of the fact that at least above 4 degrees, water is normal. It's a normal liquid. As you warm it up, it gets less dense, at least above 4 degrees. Now, oceans stratify also, and you'll recall that this is the density temperature profile for water, density temperature relationship for seawater. And like a more normal liquid, regardless of what temperature you start at, if you warm it up, it gets less dense. So lakes stratify, the ocean stratifies, saline lakes, which can be much saltier than the ocean, stratify, because as you warm them up, the water gets less dense. Okay. How deep is this thermocline going to be? How thick is the epilimnion going to be? If we define the thermocline as the depth of greatest temperature change, on this diagram, I think it's about here, maybe right here where the RTR is the greatest. This would be the planar thermocline, the specific plane, the depth at which the temperature is changing the most rapidly as you go down into the lake. The place where this curve is the steepest. If we define that as the thermocline, the planar thermocline, different lakes have obviously different thermoclines. Here in this lake, it's like around 4 meters. In these lakes here, down around 20 meters, 15 meters. What is it that causes different lakes to have different thermocline depths? Well, there are people who've studied this. Here's a data set worldwide, 150 lakes in this data set. They found that you can predict the depth of the thermocline, the planar thermocline, the depth of the thermocline pretty well based on only one variable, surface area of the lake. Now, A is area. An exponent of 0.5 means an exponent of 1/2 means square root of area divided by something. Well, obviously pi r squared, if it's a circle, the square root of area is going to be related to the radius of the lake. The square root of the area is going to be related to the fetch of the lake. And it's a little complicated, unnecessarily complicated looking model, right? So they're going to take something related to the fetch of the lake, divide it by something, and take the natural logarithm of that and raise it to a power. Okay, it's complicated, but the basic fact is there's only one geographical variable here, the area of the lake. And obviously, despite all of the complexity surrounding it, if the area of the lake is bigger, in this formula, you're going to get a bigger thermocline depth. And the R squared, the amount of variation among lakes that is explained by this formula alone, is about 2/3. About 2/3 of the difference in thermocline depth seems to be explained simply by the area of the lake. Now that's worldwide, and there are a lot of lakes at a lot of different latitudes and a lot of different kinds of situations. So it's pretty impressive that using area alone is going to give you that high a correlation. But I think you'd expect a higher correlation looking at a smaller set of lakes where there's less uncontrolled variation. So for example, we might look at lakes in Cameroon, which we're going to talk about Cameroon a little bit later today, which is in Western Africa, kind of a mountainous region. They've got a bunch of lakes there, a surprisingly, I think, large number of lakes, many of which are like volcanic in origin, like crater lakes and stuff. In a set of 52 lakes, using one variable alone, that variable in this formula explained about 83% of the variation among lakes in thermocline depth. Okay, when you look at, and what is F in this formula? That's right, fetch. When you look at all of these different studies combined, what you notice is that the variables that explain thermocline depth are area, maximum length of the lake, maximum effective length, maximum effective width, fetch. These are all the same thing, really. When you see area here and it's a square root of area, we're really talking some version of fetch. The larger the lake, especially the larger the fetch, the deeper the thermocline. And that makes complete sense. If you've got a small sheltered lake, there's not as much wind energy on the surface forcing the mixing as if you have a big lake. Thinking about when lakes mix and when they stratify, what this is showing here is lakes in different parts of the world, ranked from left to right based on how cold they are, cold, mean annual temperature below zero, below freezing Celsius, to very warm, mean annual temperature like in the 70s Fahrenheit over here. You see that there's a pretty strong negative relationship. The colder it is, the later in the year, the lakes stratify. The warmer it is, the earlier in the year, the lakes stratify. As you might imagine, lakes in colder climates are much more likely to be dimictic. You see the dark dots, these are dimictic lakes. That is to say, they freeze in the winter. Lakes in warmer climates are much more likely to be monomictic. That's these open circles. And there's kind of a sweet zone in the middle where some lakes are monomictic and some lakes are dimictic. You might recognize some lakes on here that you have heard of. So for example, what do you think this extremely cold lake is? Way over here. It doesn't stratify. Summer doesn't really begin until the middle of July. That's right, this one is Lake Baikal. At the other extreme, down here, we've got Lake Kinnerets. In the Middle East. And in the middle, let's see if we can find, where is Minnesota? Mean annual temperature in Minnesota, it's about 10 degrees, 50. Colder in the northern part of the state, warmer in the southern part of the state. So Lake Shagawa is right here up in Ely. And Lake Mendota in Madison, which is south of us, is over here. So we got Michigan, Minnesota, Wisconsin here in the middle, Siberia at one end, Africa and the Middle East on the other end. Some lakes never, in contrast, some lakes never stratify in the summer, or they stratify and then they mix again. They stratify and they mix again. You know, and basically a lake that is too shallow, it's too shallow to really stay stratified. It'll maybe, you know, you got a 2 meter deep lake, 6 feet deep. Is that even a lake? It's probably not a lake. And a wind blows and it'll just mix it all the way to the bottom. So a polymictic lake, lakes that mix multiple times in the summer, maybe they stratify, but you know, a windy day will mix them all the way to the bottom and then we say they're mixing. Well, what is the depth that determines this? Well, if you look at a bunch of lakes of similar climate, Ontario, Poland, and Minnesota, what you see is that for a given length, like fetch of the lake, that's the x-axis, there is a particular depth that's kind of the cutoff between stratifies in the summer like a dimictic lake or repeatedly destratifies in the summer. And that's kind of what this graph shows. Above the line, these lakes are basically consistently stratified in summer. And below the line, they're consistently destratifying or often destratifying. So we might say these lakes were polymictic and these lakes were dimictic. Okay, and I think that's the end of this section of things where we're really talking about stratification of lakes in the summer. And the next topic is ice cover, winter. So I think we've talked about what makes lakes stratify and what determines the depth of the thermocline. The next big topic I want to go to is lakes in winter and ice covered. And I'll leave this graph for you from last year. You might want to look through your notes and see if you can find the temperature profile that you measured earlier this year for Round Lake and Phelan, which hopefully you measured at least 1 meter intervals or at most 1 meter. This is since you have the capability of measuring, like this one shows, at half meter intervals. You'll have some nice data. What we're going to do now is take our halftime break, and we're going to come back and talk about lake ice, temperature profiles, and isoplyth diagrams, and we're also going to talk about what we're going to do on Thursday. So I'm going to stop sharing, and I'm going to hold up my hands and go 10-minute break. All right, welcome back. Sorry for the, okay, only 2 minutes, but I'm having a little pet crisis upstairs. We got this old cat. Then we got this kitten. Who knew? We thought they would get along. No. Anyways. All right. Well, let's see. Oh, look, I wrote a question on the board. Let's see if you can tell me the answer to this question. There are 3 ways that heat can get from one place or object to another. Like, let's say that I'm cold and there's something like, here's a cup of coffee, something warm over here. What are the 3 ways that heat could get from over here to over here? There are 3 ways. Can you name all 3 ways? Now, one of them has 2 different names, so you won't all have exactly the same answer, but can you put it in the chat? What are the 3 ways? However many of them you can name. What are the 3 ways that heat can get from one place to another place? From one object to another object. All right, I got all 3 names. Here we go. Right, obviously I can just touch it. Right? And the vibrating molecules here, because it's above absolute 0, the vibrating molecules here vibrate against my hand, transferring heat energy to my hand. So my hand, which is a solid, well, and a liquid, it's got a lot of liquid in it too, right? Touching this object, so it's actually touching. The molecules here are touching the molecules here, touching the molecules of my hand, and actual slamming of the molecules transfers energy. Which of those is that? That's conduction. That's conduction by the warmer molecules actually touching, having contact with the colder molecules and transferring the heat, so then they're all moving at the same heat, right? So that's conduction. All right. What about the fact that, this is warm and I could, put my hands out like this, if it was a fire or that hot heater, it's just hot. And I put my hands out like this and I catch the heat on my hand. Well, obviously there's energy going from that to my hand. What is this one called? This way that heat gets from the hot object to the cooler object. What is that one called? No, good guess. It's not conduction and it's not convection, it's radiation. And radiation is carried by electromagnetic waves, right? Energy that's conveyed, heat that's conveyed by electromagnetic waves. I mean, these carry energy from one place to another, but they are not molecules going from one place to another. They're just waves of energy. Conduction is when it's conveyed by actual touch of the objects or the materials. However you want to think about it. The vibrating, moving, energetic molecules are touching other molecules, and that conveys energy. Or they could be radiating, emitting electromagnetic waves, or here's some heat here, there's some heat there. How is that heat going to get from there to there? Oh, look. Yeah, it moved. Okay, that's kind of weird because that's not a natural thing, but if the warm water actually literally moves, it carries the heat energy with it. That is called advection or convection. Oops. And I put convection in quotation marks because sometimes convection is used with two different meanings. In the way that we're using it on this list, it just means heat that is carried by a moving fluid, heat carried by a moving substance.
Professor, you might have to adjust your camera a little. We can't see the bottom part there.
Yeah, I'm gonna put it down to give you the rest of it, right? So heat that's carried by a moving fluid, whether that's a solid or a liquid or a very slow moving, a liquid or a gas or a very slow moving solid, like I don't know what, glass or something. That's one way to think of convection. Convection is also used in the situation in which the difference in heat causes the water movement. Yeah. So convection in the general sense is heat that's carried by a moving fluid. Convection in the narrow sense is heat that's carried by a moving fluid where the movement is caused by the difference in density. So if you heat some air up and this causes the air to rise, and that causes other air to sink, this circulation is caused by convection in the narrow sense. It's also carrying heat with it, meaning the heat is going with the movement. Convect, like a vector, like a directional movement. If the heat is going with the movement. Many meteorologists and climatologists use the word advection on this list. And they use the word convection only for this specialized category. But obviously, convection is not the only thing that causes water movement. I mean, if you've got, a convection oven. Anybody ever heard of a convection oven? Is that a no? Yes, you've heard of a convection oven. Yeah, here's the weird thing about a convection oven, right? They have fans. They're actually advection ovens. My regular oven, it's got heating elements in the bottom of the oven. Where are the heating elements? The top for broil and the bottom for bake, right? It heats the air moves up. That's a convection oven. My oven already is a convection oven. You pay a lot of money for a convection oven, what are you getting? An advection oven. Yeah, I don't know. It's just a complete mystery. I mean, how do you separate these words? So, typically meteorology, climatology will be really specific. We'll say advection is heat, is a mode of heat transfer. It's when the heat is carried by a moving fluid. Lots of different things can cause fluids to move. If the reason the fluid is moving is because of a difference in heating, warm air rises, cold air sinks. If that's what's causing it to move, then we call it convection. My guess is you were taught convection and that you were not given a clear explanation of the difference here, and that it'll be really hard for you to separate those two. Now, okay, not all of you, but some of you. So I kind of think it's like a lost cause trying to get you to use these words correctly. So if you say convection when what you really mean is advection, I might correct you. Okay, but I want you to at least understand these 4 concepts. There are 3 ways that heat gets from one place to another. Carried by a moving fluid, that's advection. Transferred from one to the other by direct touch of the molecules, that's conduction. Carried by electromagnetic waves, that's radiation. And then the 4th concept, fourth, whatever finger you want to use, the 4th concept is sometimes water movement is driven by a difference in density, and that's convection. Okay, so we got 4 words. Hopefully you got all 4 of them. Let's look at how these apply to lakes. I'm going to shift to my second PowerPoint here, which I just posted. I realized I didn't post it last night. I just posted it. So if you like having, your own version of the PowerPoints, that is now posted. And whoop, Jeffrey says, you're not sharing anything. Here we go. Let's see, can we see that? There we go. All right. I like to draw on the board when I do this in a classroom, but hopefully it'll work better just PowerPointing it today. We'll see how it goes. So what's the topic here? Lake ice. I want to cover heat fluxes, which is to say the flow of heat, the temperature profiles in the ice, and ice cover growth, the growth of ice cover, and the decay of ice cover. Ice cover increasing and then ice cover decreasing, the thickness of the ice. So it's kind of these 3 topics. And it's all connected to heat. All right. First of all, I'm going to show you a bunch of sort of diagrams that look like this. What I've done is I've put liquid water here. I've put the ice that's floating on top of the lake here. And then above that, we've got the air. I kind of drew some sky up here. Here's a cloud. The sun is kind of implied up there, but not shown because it's pretty far away. And there's air and a breeze. Okay, what are the major ways that lake ice, that heat moves into, out of, and through lake ice? Okay, first of all, sunlight is the major source of heat. Sunlight radiation strikes the surface of the ice. Some fraction of it is reflected. The fraction that is reflected is called albedo. Some of it is transmitted. It enters the ice and it travels through the ice. And depending on whether the ice is clear, black ice, in which case it's just as transparent as water, or maybe it's white, gray ice made from snow that flooded, in which case it's about as opaque as snow. But in any case, some of the sunlight is reflected, but some of it is transmitted through the ice. And that's a major source of heat for ice. Now, the sky above us is not absolute 0 in temperature. The sky above us is air. Above you is miles and miles of air, mostly nitrogen gas, but also water, vapor. Oxygen is a big component of the atmosphere, and those things are all above absolute 0. Because they are above absolute 0, they radiate. They radiate electromagnetic radiation. Now, the sky is not as hot as the sun. The sky is actually, often colder than the surface of the Earth. So as you might imagine, the wavelength of light that is radiated by the air is pretty long wavelength. It's too long wavelength for our eyes to sense. It's basically infrared, maybe even long wave infrared. So I drew a cloud to represent the atmosphere, but it's not just the clouds. Clouds are droplets of liquid water. Clouds are not surrounded by nothingness. Clouds are surrounded by air, nitrogen, oxygen, water, carbon dioxide, right? Molecules that are above absolute zero. The atmosphere as a whole radiates energy in all directions, some of which is radiated down and received by a lake. Another way that lakes take in heat is by warm air. Well, air that's warmer than the ice anyways, blowing across the lake. And the movement of warm air from, say, the shore over the lake is advection. And where the warm air touches the ice, heat is directly transferred by conduction. So there probably should also be the word, maybe a horizontal arrow showing the advection, and maybe I should have labeled this vertical arrow conduction. So these are the three ways that ice gets heat from above. Solar radiation from the sun, atmospheric radiation from the sky, and then conduction from warm air that has advected across the lake from somewhere warmer. Lake ice also takes in heat from the water that is below it. One thing we know about the ice is that it is always 0 degrees or below. One thing we know about the liquid water is that it is always 0 degrees or above. So most of the time, maybe even all the time, most of the time the liquid water under the ice is warmer than the ice itself. If this water is warmer than this water is liquid, this water is solid. This water, when the two of them touch, heat will be conducted from the liquid water into the solid water. This can be a substantial source of heat for ice. Ice is constantly receiving heat from below. Okay, so these are the major heat fluxes for lake ice. You could also, there's also radiation that goes in within the lake, but it's not a big deal. There's also convection of water under the ice, and the advecting of the warmer water does carry heat towards the ice, but it's not as big an issue. And of course, within the ice itself, heat is conducted from wherever the ice is warmer to wherever the ice is colder. Okay, so here we've got our three ways that heat can get from one place to another. And here are the ones that are really important for lakes. All right, what are the consequences of this? All right, let's say that it is a cold day in winter. And by a cold day, I mean the air temperature is far below freezing. A cold day is a day in which the air temperature is far below freezing. What this means is that the surface of the ice is probably going to be close to air temperature. So the temperature profile for the ice is going to have something far below zero at the surface of the ice. Now at the bottom of the ice, it's going to be meeting liquid water. So where the ice meets the liquid water, that temperature is going to be zero. So here we have the bottom of the ice, zero. Now what's going to happen here? It's cold up here, far below zero. It's warm, relatively speaking, down here. It's above zero. So this is warmer, this is colder, and the ice is in between, like literally. So what's going to happen? Heat is lost out the surface of the ice, and heat enters from below, and the heat flows through the ice. Heat flows from the warm water under the ice, through the ice, and out the top to the sky. Now, it could be warming, typically the air that's drifting it away. It could be radiated. Well, it is radiated, but a major source of heat loss from the surface of the ice on a cold day is advection. And the cool thing is, the interesting thing is that heat is being conducted through the ice from the warm underside of the ice to the cold top side of the ice. Well, what happens to this heat? The heat that is in the liquid water that is getting conducted through the ice and then into the ice and then through the ice and out is lost. This water that's right under the ice loses heat. It loses heat to the ice. And what happens to it? It freezes. So the normal situation of things on an ice-covered lake in winter, January, February, on a cold day, heat is being lost out the surface and liquid water is freezing onto the bottom. So the ice sheet freezes downward. Lake ice is made out of lake water, and lake ice freezes downward. It thickens by getting thicker and thicker and thicker downward into the lake. So what's the temperature profile? On a cold day, it's going to be very cold at the surface. It's going to be zero at the bottom. Right near the ice, it's going to be near zero. But as you get away from the ice, you recall there's very little resistance to water movement under the ice. Or maybe you don't know that. There's very little water resistance to mixing under the ice because it's basically all the same temperature under the ice. And so under the ice, it tends to be very well mixed, pretty much isothermal, except right next to the ice where the temperature drops rapidly. Okay, that's a cold day. Those are the major heat fluxes on a cold day, and this is the temperature profile that it causes. Now, let's look at some real data. I'm going to show you some graphs from this paper. This is from I think these are master's students of Heinz Stefan at the University of Minnesota, who's a limnologist in the civil engineering department. And what they did was they took a bunch of temperature sensors and they froze them into an ice sheet on a lake. And they had a data logger up on the surface. And it tracked the temperature profile within the ice, like every hour during the course of a winter. So what we have here is above this dotted line is the air. Below the dotted line is inside the ice. So this is 1 day's worth of data. So the line labeled A is midnight, well, 11 p.m. The line labeled B is 3 in the morning. The line labeled C is 7 in the morning. So here we have midnight. The air temperature was minus 16 degrees centigrade, 16 degrees Celsius, right? And then it got colder, and then it got colder, and then the sun comes up, and then it starts getting warmer. So here we have midnight, 3 in the morning, 7 in the morning, you know, the temperature, the air temperature dropping. Then the sun comes up, and by 10 in the morning, here's the air temperature. By noon, here was the air temperature. By 2 in the afternoon, by 4 in the afternoon. And typically in Minnesota, about 4 in the afternoon, 3 or 4 in the afternoon is typically the highest temperature of the day. And after that, the temperature starts going back down again. So up here, you see the air temperature in one day going up and down. And you can see that at the surface of the ice, here's the temperature at midnight, here's the temperature 3 in the morning, here's the surface of the ice, the temperature of the surface of the ice at 7 in the morning. And then the sun comes up and the temperature at the surface of the ice goes up. Yeah, see that? Now this is all below freezing. This is a whole day when the temperatures are below 0 Celsius, so below freezing. You can see that the temperature at the surface of the ice is tracking the air temperature. It's not as extreme. It doesn't get as cold as the air temperature does. But it's dragged down and then back up again by the air temperature. We're tracking the air temperature, following the air temperature. Now at the bottom of the ice sheet, so here's all this ice, at the bottom of the ice sheet, or their lowest temperature sensor, it stayed at -2. Now I'm not really sure why it didn't go all the way to 0. I think this is simply the deepest temperature sensor that they had embedded in the ice. And you can see that from day to night to day to night, the surface of the ice changed temperature. But down in the ice, like 35 centimeters down, the temperature of the ice was not changing. And in between those two, at least at night and in the early morning, was basically a straight line. Okay, so if you can compare this actual data to this kind of cartoon here of the temperatures within the ice. So this is like a cartoon, sort of a pure theoretical line. And you can see that in the 24-hour day, a lot of the time, it really matches that line, that description. All right, well, not every day is a cold day. Sorry, let's look at that in a little more dynamic, right? Just like I said, at the surface of the ice, the temperature goes up and down and up and down and up and down. So here we've got like a week in the life of this ice sheet. And you can see that at the surface of the ice, the temperature goes up and down and up and down. Every one of these is one day. Here's like mid-afternoon. Here's like, 3 in the morning. Mid-afternoon, 3 in the morning. So 7 days, 7 ups and downs. This is the surface of the ice sheet. Meanwhile, at the very bottom of the ice sheet, the temperature hardly changes at all. Okay, so this is what's going on inside the ice sheet on a cold day. This is a winter, and even the daytime highs are below freezing. All right, what about a warm day? What about a day when the air temperature is above freezing? Okay, so let's say that the air temperature is above freezing, the sun is shining, there's going to be a net flux of heat in. Now there's still going to be heat lost from the ice by radiation because the ice is above absolute 0. But the combination of all of these factors leads to a positive flow into the ice of heat. So the surface of the ice will be warm, maybe even melting. So the surface of the ice will be 0. The bottom of the ice, of course, is 0. The coldest part of the ice is going to be right in the middle. If this is the coldest part of the ice, then heat will be flowing from the liquid water upward in towards the middle of the ice. And heat will be flowing downward from the surface into the middle. And you end up with a temperature profile that looks like this. At the surface of the ice sheet, it's 0. At the bottom of the ice sheet, it's 0. But in the middle of the ice sheet, that's where it is the coldest, the farthest below freezing. And then, of course, under the ice, you have that, really close to the ice, it's really close to 0. But as you get away, it rapidly warms up to whatever temperature is under the ice. So you can see this is a very different pattern of flow of heat. Instead of the heat coming in the bottom, flowing through the ice and out the top, now you've got heat flowing into the ice from both directions. Well, how does this compare to some real data? Let's go back to that same paper and the same data. Here we have a different day, and you can see here is 0. So this is a much warmer day, or a mild, sunny day. At night, midnight, well, what do we got? 8:03 in the morning, 5 in the morning, 9 in the morning, 11, noon, 1, 2, 3, right? In the afternoon, right? So the air temperature is 10 below, but by the middle of the afternoon, the air temperature is right near 0. The surface of the ice follows the air temperature pretty closely, and that makes sense because it's touching the air and, and so on. And the bottom of the ice stays anchored, as you see. So here in the middle of the day, 11, 12, 1, 3 o'clock, middle of the day, where is the coldest part of the ice? Right here in the middle. Colder at the bottom, colder at the surface, warmest right in the middle. What is it like at the end of the winter when the ice is rotten, as we say, or black, as some people say, or gray? Well, this is what you've got. You've got heat coming in from this above, from the air and the sun. You've got heat coming in from below, from the water, which is liquid and therefore above freezing. And at some point, you get ice that is basically 0 degrees top to bottom. 0 top to bottom. Now, at this point, what you're going to have is any part of the ice that was a little bit saltier is going to melt because it's already 0 and the freezing point of ice is even lower. So if the temperature is 0, the pure water will stay frozen, but any kind of salty parts of the ice will melt. The ice will be melting upward from below, getting thinner and thinner, but at the same time, it will be riddled with liquid water. Channels of liquid water intermixed with a spongy structure of solid water. At this point, the reason we call it rotten is because it's weak. You can break it easily. Remember the last time we were at Round Lake, at least in the latter 2 groups of people, we pulled some ice up out of the lake and you could just see how it was riddled with channels and holes filled with water. Solid ice, like a sponge of solid filled with water. How does the ice thickness change over time as a result of these things? Well, when the ice freezes over in November, it's thin. And the heat flows through it and out the surface. Ice is a pretty good conductor of heat. Ice is a good conductor of heat. It's like metal, heat flows through it pretty well. And the heat flows in through the bottom, out through the ice, out the top, freezing more and more water to the bottom. As the ice gets thicker and thicker, it's harder and harder for the heat to get conducted all the way out. In other words, it gets harder and harder for more water to freeze onto the underside of the ice. And so what you see is kind of rapid thickening of the ice. And as the ice gets thicker and thicker, the rate at which the ice thickens decreases. At first, it's growing very, very rapidly. And then as time passes, it grows less and less rapidly. The coldest week of the year, mid-January. So it's not like it's colder here. It's really coldest in this time period. But because the ice is thicker, the ice thickens more slowly. Because in order for the ice to thicken, heat has to be conducted through the ice and out the surface. So this is the thickness of the ice in meters on this lake. And what you see is it freezes over, the ice gets thicker and thicker and thicker, and then the ice thins rapidly and collapses. So it's not like a bell curve, it's not symmetrical. It's a funny sort of almost like reaching an asymptote and then crashing like a sawtooth, like a gradual slope and then a rapid decline. And that's pretty much what we saw. I think by the time we got on the lake, there was about 40 centimeters of ice on it. And it really didn't matter how cold it was. It stayed about 40 centimeters. Maybe it was a little under 40 when we first started. And then maybe it was a little bit over 40 right after that really cold week. But it wasn't a huge difference. But then once it started melting, the thickness decreased rapidly until at some point it collapsed. Now this is showing some theoretical models based on actual climate data for a particular lake in a particular year, compared to the data points which were the actual observations of the ice thickness. Let's just look at a couple different years just to show you how the model and the theory applies to some like real data on a real lake. And here we have ice thickness over time, rapidly increasing, kind of leveling off as the ice gets really thick, and then collapsing rapidly when it warms up. And this is December, January, February, March, April. Do we see this in the diagrams in the textbook? So what I've shown you in this little PowerPoint is not in the textbook. I've been working with lake ice for 20 years now. Am I that old? I guess I am. I've been working with lake ice for a long time. It's one of my research areas of research. Yeah, I mean, I'm going to work on it on my sabbatical next year, so I'm pretty excited. Anyways, so I got a lot of information about this that's not in your textbook. So that I just shared that with you. And Minnesota, of course, is a hotbed for lake ice research. Yeah, because we have a lot of ice and a lot of limnologists. But here's a textbook. Here's two diagrams for your textbook. First of all, here's ice thickness on Moretta Lake. This is a lake in the Arctic. This is a monomictic lake. It only mixes one time a year. So we got the months along the horizontal axis. Lake depth is the vertical axis. And these numbers show you the temperature. What we're looking at right now is the ice thickness. And you can see in January, there was a meter of ice. By the middle of April, there was like almost 2 meters of ice, 6 feet of ice. And this is in the Arctic. And you can see the ice thickening, getting thicker and thicker and thicker, then kind of plateauing, thickening only gradually, and then decreasing rapidly over the course of a month. So this is the same basic pattern. Rapid increase at first, kind of gradually leveling off, and then collapsing rapidly, thinning rapidly. Oh, I guess that was the only one I'm going to show you. So that is my little lecture on heat flow, and as the title says, heat fluxes, temperature profiles within the ice, and ice cover growth and decay. Do you have any questions about this topic? Oh, find my class. Where's my class? All right, any questions about this? Comments? Jeffrey says he's out of power. Okay, there you go, Jeff. All right. No questions. Well, okay. All right, well, let's go back to our main program here. Temperature profile under the ice and other related topics, particularly isopleth diagrams. And we will return to that Moretta diagram soon. Let's go here. There we go. Okay, so here's a temperature profile from Lake Phelan. Collected 2 years ago, 3 years ago now, in March. And you know, we couldn't measure the temperature of the ice. Yes, June, you have a question?
I can't see what you're showing us.
What? Oh, right. Let's see, I have to. Here we go. Switch shows, here we go. All right, so temperature profile Lake Phelan. We couldn't measure the temperature in the ice because we just drilled a hole in the ice and there was water there. So we just used 0 as the temperature. Under the ice, it warmed up very rapidly. So 1 meter under the surface of the lake, and the temperature was 2.1. And it was basically 2.1 all the way down to 3 meters. Then for some reason, a little bit colder. And then it was a little bit warmer, and then it was basically 2 degrees, a little bit, maybe 1/10 of a degree warmer at the bottom. So I'd like to point out that, you know, we measured this, and the temperature under the ice was 2. It's a myth that it's 4. It could be 2. It is 2. We've seen it. Whoop. What's all these things? Okay. What temperature is it going to be under the ice? Well, it's going to be whatever temperature the water was when the lake froze over. So if it's a really, really windy place and it's really hard for the ice to get started, then the lake could just keep cooling down as the wind blows in December. If, on the other hand, it's a very sheltered, small lake, all it takes to freeze is a calm, clear night. And the water at the surface of the lake loses heat to the sky. And if that very top layer of water freezes down below, cools down below 0, it will freeze. Then all of a sudden, you've got ice on top of the lake. If you've got ice on top of the lake, a little bit of a breeze is not going to circulate the water. Now, if it's a windstorm, it could break the ice up, you know, if it's just a thin layer. But a lot of times what happens is we'll get a week of fairly low wind, and then a storm will come through or whatever. If the lake freezes over and nothing breaks the ice up, the ice will thicken rapidly. And the thicker the ice is, the more resistant it is to getting broken up by the wind. If you have a small little lake, it might freeze over at the surface, you know, when the temperature is really quite warm. If the wind is not mixing the water and the surface freezes down, cools down to 0, so you've got ice, ice floats. Ice will float on top of water of any temperature. I mean, you could take an ice cube and it will float in water that's almost boiling, right? So ice is so much less dense than liquid water that, you know, once you've got ice on the surface, it will float. Now, under the ice, if the water is quite warm, you know, it may circulate, and the water right under the ice sheet maybe 1 to 3 degrees Celsius. If the water deeper in the lake is less dense than that, then it will circulate. And this will gradually cool the lake water down. So if a lake freezes over when the water is more than 4 degrees, that can happen. But the convection under the ice will gradually cool the water down until it is 4. Well, so lakes can freeze over with the water being a variety of temperatures, typically 4 or less, but not necessarily. Well, what temperature will it freeze over at? Well, it depends on how windy it is and how big the fetch is. So this is a bunch of lakes in Wisconsin. I forget what the sample size is here, 30 lakes or 40 lakes, kind of in the same area. And what we've got is lakes of a bigger fetch are on the right. And this is probably, Winona and Mendota and Monona in Madison, these bigger ones. Smaller lakes are on the left. And what you see is that the bigger the lake is, typically the colder the water is under the ice. This is the lake temperature when the lake froze over. And you can see that for lakes that are above, I mean, this is a fetch of 1 kilometer. So that's a pretty darn big diameter lake. So these are lakes are 8 kilometers in fetch. Actually, I don't think that is Mendota. Anyways, and you can see these lakes are 1 degree Celsius when they froze over. Smaller lakes, 2, 3, even up near 4 or above 4 when they freeze over. Okay, so that's what this is showing. And now we want to move to our next topic, which is, I want to teach you how to read a particular type of limnology diagram that is known as an isotherm diagram. All right, here we go. This is a skill that I would like to teach you, how to read diagrams like this. Now here's Lake Moretta again. And an isotherm diagram like this is constructed from data like you would collect. So you would go out there, in July, in August, in September, and measure the temperature profile. Let's say that we went out to this lake on August 1st. What was the temperature profile on August 1st? Move that away. Let's see, here's August 1st, right? Here's August 1st, and it's pretty clear that on August 1st, this lake was 7 degrees from top to bottom. So here I'm going to put August 1st here. 7 degrees, top to bottom. Can you see that? At the top of the lake, it's in between the 7 line and the 7 line. It was 7. At the bottom of the lake, down here at 9 meters, the temperature was in between the 7 and the 7. So it was 7. And there doesn't seem to be any difference all the way top to bottom, same temperature, top to bottom. Sorry. In contrast, let's look at February 1st here. February 1st here. So here's February 1st. What do we see? Well, the top meter is ice, and we don't know what the temperature is. 2 meters down, the temperature is between 1/4 degree and 1/2 degree. 3 meters down, the temperature is between 1/2 degree and 3/4. 4 meters down, it's between 3/4 and 1 degree. At 6 meters depth, it's a little bit beyond this 1 degree line. So just short of 6 meters depth, the temperature was 1 degree. And these lines are all pretty evenly spaced up here. You know, it's not like it changed temperature rapidly right under the ice. It's kind of looks sort of like a very gradual increase. So I think that the diagram kind of looks like this. Right under the ice, it's 0. And 6 meters down, it's 1. 6 meters down, it's 1. And it's a little hard to tell whether the temperature keeps rising at all beyond that, because it's all simply in between lines. So it might look something like this. The way that they construct an isoplex diagram like this is by going out to the lake on a variety of different days and getting temperature profiles on different days. And then you take a sheet of paper, or a piece of graph paper or whatever. And for each of the days that you collected the data, you mark the temperatures at all of the different depths. And then you connect the points. And then typically you erase the original data points, so all you have are these lines. So if we were to go to, you know, the 1st of April, it would be very similar looking. Let's say that they went out on the 1st of April, and that was the data they collected. The ice was 2 meters thick, and at the bottom of the lake, it wasn't even an entire degree in warmth. So on that date, let's see, the ice was 2 meters thick, so it starts here, and it wasn't even 1 meter depth, so the temperature profile probably looks something like this. Okay, so when you look at a diagram like this that's an isopleth diagram, isopleth means there are lines that connect equal values. Iso meaning same value. So on this date, maybe it was 7 at the top and 7 in the middle and 7 at the bottom. And so there is a line connecting all of the 7-degree temperatures. In the wintertime, maybe in the beginning of January, it was half a degree at 2 meters. By the beginning of May, it was half a degree at 5 meters. So you can imagine a bunch of half a degree measurements on this diagram, and they drew a line connecting the half a degree temperatures. This enables you to see the big picture of what the pattern is for a lake. I think you can see that, for example, if we were to look let's see, early July, what I'm gonna do here, I think you can see that the temperature was, you know, somewhere around 4 or 5. So here's pick one of those dates, the temperature profile looks like that. Here's the middle of summer. And then let's put down a line for after. So let's say end of August. By the end of August, the temperature was back down below 4 and heading down. It was that temperature here. So on this date, if you'd done a temperature profile, it would look like that. When you put it on an isopleth diagram, it looks like this. All right. Based on the information presented in this diagram, would you say that this lake was monomictic, dimictic, amictic, or polymictic? What word best describes Moretta Lake? Would you put it in the chat? Is this a monomictic lake, a dimictic lake, a polymictic lake, or what were my other choices? Amictic, polymictic, monomictic, dimictic. Which of those words best describes the mixing regime, the annual pattern of mixing in this lake? Would you put that in the chat? Check the chat, see what people think. got one vote in, got a couple votes, okay. All right, and the votes are floating in. Desiree, Brett, Jew, who else has got an opinion on this? What do you think? What word best describes this? All right, the answer is, in fact, monomictic. I'm going to clear my drawings here and just gesture. You can see that it's monomictic because when the lines go up and down, it is the same temperature, top to bottom. Therefore, this period, this time here, the lake is mixing. In contrast, here you can see that the lake is ice covered. So here's the lake is ice covered, mixing, ice covered. When the lines are going horizontally, it means the temperature changes as you go from top to bottom. Because as you go from top to bottom, you cross temperature lines. So this is a monomictic lake. It's mixing in the summer. It's ice covered the rest of the year. All right, do you have any questions about how to read this type of diagram? Because I mean, I walked through this one and now I'm going to give you one to look at. Questions, comments? Are you still there? Hello? Okay, let's go and look at, hello? Oh, I have to annotate. All right, here is another excellent lake, Lake Kinneret. What I'd like you to do is look at this diagram and tell me, I'm gonna put you in a discussion group so you can like talk it through a little bit. When is this lake mixing? When is this lake stratified? When is this lake ice covered? If in fact it ever mixes, does it mix? When? Is it stratified? When? Is it ice covered? When? And based on that, what best describes this lake? Monomictic, dimictic, polymictic, amictic? Yeah. Okay, so here we have this diagram. This is also in the textbook if you want to look at your textbook version of it. Hopefully one person in each group has a copy of this diagram. And I'd like you to look at this diagram and tell me, what can you tell me based on this diagram? All right, so take a look at this diagram and tell me what you can say about it.
Do you have a copy of it?
Yeah, I do. Do you want me to share it?
I'm looking at it also, so that's all right.
Sorry.
I'm looking at it too, so
Oh,
I'm good.
okay.
So are the straighter ones down? Is that mixing?
Yeah. So if it's like straight and it just has like the first two that say 16, that just means that it's mixing because it's the same temperature throughout.
Oh, okay, that makes sense. So then it would be what?
It mixes in the winter time. And like,
That's
yeah,
that's not ice then in the summer, is it?
it could be.
I wonder where Kinneret is.
But this also looks like a monomictic lake. Is that
Is it, or would it be dimictic since it mixes twice? Because there's two sets of like straight lines.
well? Are you talking about the straight line and in March?
Oh, shoot! Yeah, there's 2 years.
I don't really know what to think about this lake though. No, yeah, I would say I would stick with monomictic. Yeah.
Yeah, because the second straight of lines is just at the start of the next year.
Right.
So yeah,
Just weird how
monomic,
15 is all over the place on the second year.
yeah. Oh, that is weird. So then we get ice around like what, May to June? Is that about?
Yes. Well, what is the water temperature? So the temperature of the water, that's 16 degrees Celsius, right?
Oh yeah, okay, that is the temperature.
So then it looks like it gets
Warmer.
warmer throughout the year, right?
Yeah.
Because that says like the middle section where it looks like it gets the hottest is it's saying 28 degrees Celsius. And that's closer to the top.
Yeah. So if it's mixing, does that just mean then like that middle part, like during the summer, is stratified?
Yeah.
Okay. We wonder that. So is there no ice cover ever, or does it?
Maybe there's no ice cover. Maybe it's like a you know, no. I was gonna say an algae thing. It probably isn't that, but you know when it's just harder to mix it if it's not. Maybe it's a really deep lake. I don't know.
That could be it. Well, it is depth below
The
Wait,
sea level.
Hmm.
That doesn't really help though.
Yeah, no. Wait,
Whoa, okay. But on the like, do you have it open in your textbook at all?
oh no, I just have the PowerPoint pulled up.
Okay. I don't know why, but it's saying that the lake is located well below sea level. So I don't know if that means anything. Probably not, but I don't know.
Yeah, because it's in.
But if there was like ice formation, then you would see numbers closer to 0. But instead it's just,
So no ice and monomictic.
yeah,
Okay,
this doesn't feel right.
doesn't feel right.
But it's the picture is right when it starts talking about warm monomictic lakes.
Oh,
So
okay.
it's
That's
probably, it's like tropical is what they're saying.
Well, this is a very different looking lake, isn't it? So the first thing we're going to do is look and see, does this lake ever mix? And if so, when? And I would say that looking at this diagram, this lake looks to me like it is mixing here. Maybe January, February, March. It's mixing. And you can tell it's mixing because it's the same temperature top to bottom. So even if it's not literally mixing, there's no resistance to mixing. But also, you know, this bottom water here used to be between 16 and 17 degrees, right down here. And now the water is 14 or 13. So it's clear that water has mixed down and changed the temperature at the bottom of the lake. Now, you look at the rest of the year here, and you notice that in this whole period of time, if you were to start at the top of the lake and go down, the temperature would change. Like if you were to look at this in particular here, look at this. The top 10, 15, 20 meters of the lake, it's all the same temperature, like 27 degrees. And then below that, look at this, the temperature changes very, very rapidly as you move. As you go down deeper and deeper in lake, the temperature drops rapidly. And then below about here, it's all, you know, about 16 degrees. So it's clear that this is the epilimnion, this is the hypolimnion, and this is the metalimnion. Anytime you're seeing these kind of horizontal lines, and you know the lake is stratified. So it seems to be stratified from about April to maybe December. Is this lake ever ice covered? No, this lake is never ice covered. I mean, this lake is never colder than 16 degrees Celsius. So this lake is never ice covered. All right, based on this information, how would you classify this lake? Is this monomictic warm, monomictic cold, dimictic, polymictic, or amictic? What best describes this lake? Yep, this is a monomictic warm lake. This is actually a reservoir. The surface of this lake is 200 meters below sea level, right? So this is this is the Dead Sea, I believe. And the surface level fluctuates because it is a reservoir and there's so much evaporation. Anyways, moving on. You'll notice at the bottom, the temperature of the water at the bottom of the lake does change. It changes when the lake is mixing. It doesn't change a lot, but it changes enough to tell you that water has gotten down there from the surface. So therefore, we know that, or suspect, that this lake is holomictic, meaning it mixes all the way to the bottom. Lake Moretta that we looked at previously is clearly holomictic. If you look at the water at the bottom of the lake, it's down near zero, down near 1 degree. It warms all the way up to 7 and then cools back down again. It's clear that the lake is mixing top to bottom. It's clear that this lake is holomictic. A few other quick things I want to wrap up with, and then I want to just say a few words about what we're going to do on Thursday. This is showing you the ice profile on Moretta, which we looked at before, and then also Char Lake. This is a zoom in on figure 21.8, just to show you that the same basic pattern of ice gradually thickening, kind of plateauing, and then collapsing. Thickening, plateauing, and collapsing is a typical pattern. Not all lakes mix all the way to the bottom. One of the things that I was hoping we would have time to do, but the ice went out just a couple days too early, was go to a meromictic lake and do a temperature and chemical profile of it. Brownie Lake in Minneapolis is a meromictic lake that I've worked on. Lake Nyos in Cameroon is a famous meromictic lake that we'll talk about more when we talk about carbon dioxide and other chemicals next week. Temperature profile on Phelan on the left, temperature profile on Brownie on the right. When under the ice, when at Brownie, you see the temperature profile looks pretty normal. And then it starts rising again and rises all the way to the bottom. There is a chemocline at about 4 to 5 meters depth. Above that depth, the lake acts like a normal lake. Below that depth is water that basically never mixes. So this lake is meromictic and does not mix all the way to the bottom. What effect is climate change going to have on dimictic lakes? There's a bunch of predictions that were made a decade ago, which you can see them listed in CALF. I just typed this up, reading CALF. Basically based on higher temperatures, causing warmer water, later freeze over, earlier breakup, shorter ice cover duration, earlier onset of stratification and longer summer, shorter winter and longer summer, in short. But the second set depends on precipitation and evaporation. And actually what we're seeing in Minnesota is we're actually seeing more runoff. That the increase in precipitation has exceeded the increase in evaporation you'd predict from warming. But at the time that this particular study was done, these were the predictions. They're logical if you have, because of increased temperature and increase in evaporation on the land, you would get these consequences. And here's some data from Lake 226 in the experimental lake area of Ontario, which if you actually read the axes of them is pretty self-explanatory. Air temperature has gone up, the lake water temperature has gone up, the ice-free season has increased, the amount of runoff in that lake has decreased, and this has caused an increase in salinity, and so on. And that's more related to climate change, which we can talk about more. Okay, so that is what I have for you today in terms of like contents. I hope that between the CALF's explanation in writing and my PowerPoint and lecture today, you've gotten a feeling for these things. What we're going to do on Thursday of this week is we're going to do a lake ice heat calculation lab, which is something limnologists do. I will be posting the lab probably tomorrow. I want to go to Round Lake one more time to measure the water temperature and collect some algae samples. I hope to have your midterm exam, your second exam, midterm exam 2 graded. If you would like to, you could join me at Round Lake at 1 o'clock on Thursday. If you meet me there, I will give you your exam back and your lab test and answer any questions you have about doing the lab calculation. And you can help me collect some algae and measure the water temperature. I don't think that we all need to do that, but it's going to be a beautiful day. And I hate to say, oh, let's just stay home and calculate things. So if you want to meet me at the lake, and I can answer any questions you have about the lab, you can do that. If you don't want to take the time to go to the lake, just stay home and do the lab on your own. We will not meet as an entire class on Thursday. There is an optional meeting at 1 o'clock at the lake. Say, who wants to go to the lake? Is anybody going to go to the lake, or is it just going to be me? James is going to be there. Okay. And Kat's going to be there. Okay. If you want to meet me at, Round Lake on Thursday, all we're going to do is collect some algae, measure the water temperature, and I'll answer any questions you have about doing the lab. Otherwise, if you have better things to do with your time, and I know some of you have busy lives, you can go ahead and do that. Okay, so it looks like at least a couple people will be there, so I'll be there. All right, questions? Ju, is that a question?
Yeah, it is. So like, is the calculations like, just like, you give the instructions on how to do it on the manual, or?
Yeah, I will post the lab instructions, and the lab instructions tell you what you need to calculate. And the question is this. When we measured the ice thickness on, I forget what date it was, this ice was 40 centimeters thick. On such and such a date, I forget what day it was a Sunday, Monday, the ice was all gone. So a certain number of days. How much heat did it take to melt that ice? And if all of that heat came from the liquid water, what would the temperature of the liquid water be? So the water under the ice is above freezing. If the wind breaks up the ice and mixes it with the water, it melts the ice, but it cools the water down, ice water. So if all of the heat needed to melt that much ice came from the liquid water, what would the temperature of Round Lake have become? So it's really kind of it's a calculation question, but you need to understand the properties of water and the geometry of a lake to do it. So, yes.
Will there
it
be a
will
lab report then?
It's a calculation.
Okay.
So you'll actually be writing less than a full lab report. But it's like I mean, you have to write something in and submit it. Yes, and I wish I had gotten it posted before today so you could ask questions, but I'll have it posted before Thursday, and if you have questions, you can come and ask me. Other questions? Or the same question again? If that wasn't enough answer. Anybody else? Okay, well, it looks like that's what we had for today. So I will see some of you on Thursday, and I will see everyone next Tuesday. And if you have questions, you can always email me, of course. Email me questions or meet me at the lake at 1 o'clock on Thursday.